Our planet is a world of constant, slow-motion change, driven by immense forces deep beneath our feet. For millions of years, we have understood that the great Indian tectonic plate has been pushing northwards, colliding with the Eurasian plate. This colossal impact is what created the magnificent Himalayas, the highest mountain range on Earth. The long-held belief was that the Indian plate dives, or subducts, under Tibet as a single, solid slab of rock. However, recent discoveries have revealed a much more complex and dramatic story unfolding in the darkness of the Earth's mantle. It appears the Indian plate is not one solid piece after all. It is splitting in two. This remarkable process is known as delamination. Imagine a piece of bread with a thick, heavy layer of jam on the bottom. As you push it along a table, the lighter top layer of bread might continue to slide forward, while the heavy, sticky jam layer peels away and sinks downwards. This is what seems to be happening to the Indian plate. The lighter, more buoyant upper crust continues its slow-motion journey northward, crumpling and building the Tibetan plateau. But the lower, denser part of the plate is peeling off, breaking away, and sinking deeper into the superheated, molten rock of the mantle below it. This peeling action is not a clean break. Deep underground, at depths of around 100 kilometers, the plate is showing signs of immense stress. It is not just bending. It is actively fracturing, tearing, and ripping apart. This is a fundamental departure from the classic textbook image of tectonic plates as rigid, unbreakable shields. Instead, we are witnessing a continent in the process of being torn asunder from below. This incredible geological event forces us to reconsider the very nature of how continents collide and evolve over millions of years, painting a picture of a planet far more dynamic than we ever imagined. The discovery fundamentally changes our understanding of one of the most geologically active regions on the planet. It helps to explain the strange and ongoing uplift of the Tibetan plateau, which has long puzzled scientists. The separation creates a gap, a kind of wedge filled with soft, molten rock from the asthenosphere between the two splitting layers. This hot material may be contributing to the high elevation and unique geological features seen across Tibet. What was once thought of as a simple collision is now revealed to be a far more intricate and violent process, hidden from our view but shaping the very surface we live on. Uncovering a secret hidden so deep within the Earth is a monumental challenge. Scientists cannot simply drill down 100 kilometers to see what is happening. Instead, they must act as planetary detectives, using subtle clues that travel up to the surface. One of their most powerful tools is the study of earthquake waves. By placing a network of over 90 seismic stations across southern Tibet, researchers were able to listen to the echoes of distant earthquakes. They carefully analyzed how different types of seismic waves, known as P waves and S waves, traveled through the Earth's crust and mantle beneath the region. These waves behave like a medical ultrasound, changing speed and direction as they pass through materials of different densities and temperatures. The data collected over several years allowed scientists to build a detailed, three-dimensional map of the Indian plate structure. This seismic imaging revealed something astonishing. In some areas, the waves indicated that the plate was a thick, continuous slab, just as expected, but in other areas, particularly in the eastern part of the collision zone, the data showed a clear disruption. The plate appeared to be contorting, warping, and ultimately splitting apart at great depth. But seismic waves were not the only piece of evidence. Another clue came bubbling up to the surface in the region's natural hot springs. Scientists analyzed the water and found unusual types of helium gas, specifically an isotope known as helium-3. This particular type of helium is rare in the Earth's crust, but is more common deep within the mantle. Its presence in Tibetan springs suggests that there are deep fractures and cracks running through the plate. These cracks act as conduits, allowing gases from the deep Earth to escape all the way to the surface, providing geochemical proof that the plate is not intact. Together, these two independent lines of evidence, the seismic mapping and the helium gas, paint a consistent and compelling picture. The earthquake waves show a physical tear, and the helium confirms that this tear is deep enough to connect the surface with the mantle below. It was this powerful combination of data presented at the American Geophysical Union Conference that led to the groundbreaking conclusion. We are not just guessing that the Indian plate is splitting. We are observing the effects of this profound geological event as it happens, written in the language of seismic waves and elemental chemistry. This new understanding of the Indian plate is not just an academic curiosity. It has profound and urgent implications for the millions of people living in the shadow of the Himalayas. The process of a tectonic plate tearing and fracturing is an incredibly violent one. It creates new zones of weakness and releases enormous amounts of stress within the Earth's crust. As the plate breaks apart, this accumulated stress can be suddenly released, triggering earthquakes. Therefore, this discovery suggests that the seismic risk in the Himalayan region may be greater and more complex than previously thought. The ground beneath northern India, Nepal, and Tibet is being actively broken. The risk is not uniform across the entire mountain range. The research indicates that the delamination, or peeling, is more advanced in the eastern Himalayas. This corresponds to areas where the plate is tearing more significantly, creating a series of deep rifts. These rift zones are essentially lines of intense geological strain. It is logical to conclude that these areas, where the plate is weakest and the tearing is most active, are likely to experience more frequent or more powerful seismic events in the future. Understanding where these tears are located is therefore crucial for assessing earthquake hazards with greater precision. This discovery forces us to reevaluate our models for earthquake prediction. For decades, risk assessment has been based on the idea of stress building up along a single unified fault line where the Indian and Eurasian plates meet. But now, we know the situation is far more complicated. We must also account for the stresses being generated by the plate literally ripping itself apart from below. The fracturing creates new, deeper fault lines that were not previously part of our calculations. This adds a new dimension of uncertainty, but also provides an opportunity to build more accurate and comprehensive risk models for the region. While this news is concerning, it is also a vital step toward better preparedness. Knowing that this process is happening is the first step in monitoring it more closely. By expanding the network of seismic stations and continuing to analyze geological data, scientists can track the evolution of these tiers in the plate. This information can help governments and communities to media group, construction workers reinforcing building in Himalayan town, engineers inspecting earthquake-resistant structures, stocks that distribute Tinkshai equally, reinforce building codes, develop better emergency response plans, and educate the public about the risks. The Earth is sending us a clear warning, and this research gives us the invaluable chance to listen and prepare for its future movements. The revelation that a continental plate can split and delaminate during a collision is a truly fundamental shift in Earth science. Geologists have long worked with the model of continents as immensely strong, rigid blocks. We knew they could bend, buckle, and slide, but the idea that they could peel apart like layers of an onion was not part of the mainstream understanding. As one geologist noted, we didn't know continents could behave this way. This discovery opens a completely new chapter in our story of how mountains are built and how continents evolve over geological time. This new model also helps solve long-standing puzzles about the Himalayas themselves. The continued rapid uplift of the Tibetan plateau has been difficult to explain using only the classic model of subduction. But if the heavy lower part of the Indian plate is sinking into the mantle, it would create an upward force on the lighter crust above it, causing it to bob up. The delamination process provides a powerful engine for mountain building, explaining how the region can remain so dynamically active millions of years after the initial collision. It is a key piece of the puzzle of how our planet's most dramatic landscapes are formed. However, it is important to remember that this is still the beginning of the story. The current findings represent a snapshot in geological time, based on the data we have now. Science is a process of continuous discovery, and many questions remain unanswered. How fast is the plate splitting? Is this process accelerating? And is this phenomenon unique to the Himalayas, or could it be happening in other major collision zones, such as the Andes in South America? Answering these questions will require more data, more monitoring, and years of further research by scientists around the world. Ultimately, this discovery is a profound reminder of how much we still have to learn about the planet we call home. The Earth is not a static ball of rock, but a living, breathing system with immense and complex processes occurring deep beneath our feet. By continuing to listen to its subtle signals, we not only gain a deeper appreciation for the forces that shape our world, but we also gain the knowledge that may one day be crucial for protecting human lives. This new insight into the splitting of the Indian plate is a powerful step forward in that great scientific journey.